Hi everyone. Today we will be presenting amenity detection and inventory tracking with Detectron2. We're very happy to be a part of the 2024 CGPE Online Student Conference. My name is Lina and I will be doing the first half of the presentation. Moving on to the introduction. Coming to the background and summary, Airbnb connects property owners with potential short-term renters. Guests want specific amenities to get the most value of their stay. Property owners need to accurately list the available amenities as well as maintain the inventory, which can be highly exhausting. So, the motivation of the project lies within the fact that Detectron2 can analyze images and videos, performing object segmentation and labeling each pixel, which can help with object identification. So in this case, the amenities. Research demonstrates success in applications such as production and supply chain management, where Detectron2 has been used in the past. The deliverables of the project are amenity detection module, an inventory tracking module, a chatbot, and a user-friendly UI. Coming to the data engineering of the project. Firstly, let's talk about the data collection. We used 51 package and data zoo API to collect images from OpenImages v7. We downloaded a raw data set which had 30 classes pertaining to amenities that could be found in a rental property. The raw data set had about 38,000 training images, 860 validation images, around 2,400 test images, ranging to a total size of 13.8 GB. We had to merge the images with the mapped annotations and the images metadata. For data pre-processing, the steps that we followed was we had to use the API to collect the images. We chose the classes of interest. Finally, we had to separate the train, test, and the validation data sets. Then we filtered images and labels with a confidence of 1, which means that we only wanted to take those images that were 100% identified as whatever class that was uh, against it. Then we converted the OpenImages annotations into COCO formatting, which is required for a Detectron2 model training. So then we converted the relative bounding box coordinates to absolute bounding box coordinates. Finally, we created a list of the dictionaries and we pushed the data set onto an online shared drive, which was used by the teammates for further training. And then we had to register the train and the validation data with Detectron2. Here is a visual representation of the train test and the validation results that were collected. And we use the Detectron2 visualizer to see this. So we did some data analytics on the data that we collected. Firstly, we just created a histogram of the aspect ratio found in the training set and the validation set. So the ratio of its width and height of an image. And what we found out was that 50% of the images are 1.4 times wider for both train and the validation set. And here is a box plot of both the training set and the validation set, where we can see there are more outliers in the training set. And here is a visual representation of sample data. Moving on to machine learning modeling. We wanted to select two architectures. One is multi-stage and single stage to compare within the Detectron2 library. So for multi-stage, we went faster RCNN, which actually uses a region proposal network and a region of interest pooling for object detection. And it's one of the fastest multi-stage model according to literature survey. The introduction of RPN and faster RCN helps in generating region proposal networks efficiently. So this eliminates the need for external methods for region proposal generation. But the con is that training faster RCNN requires a substantial amount of computational resources. RetinaNet is a single stage and it employs a feature pyramid network for detection, and the anchor boxes are used for its prediction. So it has the least training time required and can even run on a single GPU. It's the fastest among all. It addresses class imbalance, low training times, and it's computationally the least expensive. But it performs badly with overlapping objects, especially in the presence of background clutter. So some of the improvements and innovations that we adopted for this project are, firstly, we did data synthesis through two options. One is through augmentation, where we applied some things like rotation, lighting, flipping, etc. And for data synthesis, for classes with low MAP, we tried to scrape more images and add that for only those particular classes. And then we used hypertuning based on batch size, learning rate, and iterations. And then in terms of the backbone architectures, we try to experiment with Res 50 and ResNet 101. And we did another very interesting thing called model ensembling, where we try to take the best performing custom model that we that we trained, along with its pre-trained version. We overlaid their predictions using the matplot patches library. And finally, we had an aggregated predictions at the visualization stage, on which my teammate will talk more in the oncoming slides. And one of the best innovation that we did was creating a chatbot, which provides quick solutions. It's directly integrated with the application database and can give quick results about what can be found for a particular host in that particular category. And we also have this live inventory tracking where we showed real-time detection. And this could be really helpful in terms of security and safety for rental property. Now my teammate Anisha will be taking over.
Hi everyone. So this is the architecture of the ensemble model, which is unique to this project. So as per in the image, we can see that after doing the data engineering thing, we trained all the proposed models, and out of that we select our best model. And then we also select the pre-trained version of it, and then we fuse the model results to get the final prediction. So the process of how to create the ensemble layer, for that, we first iterate over each instance detected by the first model. It retrieves the bounding box coordinates, confidence score, and class ID for each instance. Then a rectangle patch is created using patches library. The patch is positioned using the bounding box coordinates and styled with line width and edge color. The same process is repeated for the second model, and the loop iterates over each instance, creating a rectangle patch, adds it to the image, and then adds text labels to it. That's how we achieve our final prediction. Going on to the next slide. So these are machine learning evaluation results of the proposed models. So as we have proposed two models and we have explored two different ResNet architecture of 50 layers and 101 layers, and this table provides a comparison of different models based on several characteristics like mean, average, precision. So MAP is a metric that measures the overall accuracy of a model in object detection. Then comes bounding box regression loss. This metric evaluates the model's ability to accurately predict the bounding box coordinates for detected objects. So lower the loss, better the prediction. Then comes the training time. It basically indicates the time taken to train the model on a specific GPU hardware. And shorter training times are generally preferable for efficiency. Similarly, classification loss is incurred during the classification task of the model. So as per all the metrics, we have observed that faster RCNN with 50 layers proves out to be the best. Going on to the next slide. So this slide shows model loss graphs of hypertuned RetinaNet and faster RCNN. As you can see, x-axis represents each iteration and y-axis represents the loss. With each iteration, we can see loss is decreasing, which means model is learning with going on with each iteration. So these are set of images that that is observed after we trained the model and after we created our ensemble model. The first row is the image taken from our cell phone, and it's an image of a living room. As you can see, custom faster RCNN model has detected an object of pillow, and the pre-trained version detects several other instances like potted plant, book, bench, as well as TV. So in ensemble model, what we did is we fused both the predictions using patches library, and henceforth we can see all the amenities available in both the images. Similarly, for the second row, which basically belongs to outdoor amenity, which is swimming pool, then a pre-trained version of model has detected potted plant and chairs. So we kind of fuse all the outputs to get the final prediction. Going on to the next slide. Well, let's talk about web portal and overall system design of a project. So this particular system design image, you can see there are two main components, front end and back end. So in the front end, we have two main users, which is Airbnb host and Airbnb guest. Host can register their property by uploading images. And in order to do that, they will interact with the front end UI pages, which is developed using Flask, JavaScript, CSS, and HTML. So after host will upload their images, they will interact with the backend, which will have two main modules of amenity detection module, which where we have deployed our ensemble model, which will detect the amenities and will send them back to the host. And the other module is inventory tracking module, which is connected to the database, which is Cloud SQL here. And based on the amenities present in the database, we will be alerting host if certain amenities are missing. And second set of users are Airbnb guests. So they can, they can book the resort, they can book the venues based on their requirements. Going on to the next slide. Well, these are the UI pages, as you can see in the screen. So the first image is our landing page, our home page. And we can see there are two main buttons, which is host view and guest view. So in the host view, after host will register their Airbnb, they will see the detections in the second image, which is captioned as upload inventory. We see that there are, images with class labels detected. Similarly, the last image here shows the chatbot. So chatbot is basically, we have created it where if suppose there are certain questions, queries raised up by the users and guests and hosts, so they can go to the chatbot, they can ask questions, and the chatbot is capable to answer most of the questions that we have tested. I think that's all about our UI pages. Thank you so much. Thank you.
Thank you.